Greetings again, machine component designers. I'm actually in my garage right now because, well, it's raining outside and this is the only quiet place to record a lecture. So it's not very interesting, so you're just going to see the slides. Let's just review what we learned about fatigue so far. Fatigue is a type of a failure that happens when the stresses are well below the yield strength, but they're repeated, right? So it doesn't have to be a high stress, but if we repeat it enough times, there's a chance there's a failure, right? And then we said, oh yeah, what's this? Stress concentrations matter. We'll talk about those today. Here's an example. A little tiny crack starts, then spreads across the whole cross section. You can examine the failure surface and figure out a lot about what happened. So if you go to court, they'll figure out what you did wrong. Little stress concentration, little crack started at an inclusion, a stamping on a forging or a casting. Some waves caused a fatigue failure. Axle caused a fatigue failure, killed a bunch of people. We're going to take the easiest approach to this, which is the stress life method. It's the least accurate, but it's the most traditional and it's the easiest, so at least we know what's going on. Again, I can't stress enough, in your industry, in your field, you're going to need to use the technique that they use, right? But this is the general concepts. We run these, we get it as a material property. Fatigue strength is a material property based on very carefully contrived laboratory experiments, right? That gives us a material property by loading this thing in 4-point bending, pure moment, and then spinning it until it fails, right? Let's see, the SN diagram. This kind of shows on a log-log scale that there's a somewhat linear relationship between the stress and the number of cycles until failure, right? And then it's linear in this region from the 10 to the 3 strength, which is right up here, all the way down to the endurance strength, which is right down there. So sometimes this is called S3, and then this is SN down there, okay. And that's linear there. It comes from this contrived experiment again. We call that SN prime, right? SN, actually this should be SN prime here. That's a mistake. So let's change that to SN prime. All right, the endurance limit, typically 0.5, half of the ultimate tensile strength. And then we can figure out the life and the stress based on this linear equation here. What else? Oh yeah, so SN prime, right, comes from a very carefully contrived lab experiment. In the real world, with real geometry and real loading and real surface finish and necessary reliability, we have to adjust these. And I didn't really make a good enough point of this the other day, but these are all less than 1. These are all right, typically. Less than 1, right? So when we multiply these things together, the stress, the endurance strength, the actual endurance strength, so this is actual, and this is lab, right? Is much less than the lab strength. All right, and then load factor. Yeah, I didn't like this slide. I'll have to make a short video about this, I think, with some props. Well, so basically the load factor is due to the fact that the laboratory experiment comes from pure bending, which is maximized at the surface, and it's a normal stress, and it's fully reversed, right? If it's axially loaded, if that stress is axial, that stress applies everywhere, not just on the surface. So that lowers our endurance strength a little bit. If it's in torsion, that's shear, right? We know that's quite a bit less, and we've seen this 0.58 before. The 0.58, I believe, equals 1 over the square root of 3, which is the shear strength from the distortion energy theory, right? Okay, so what else? Oh, the size factor. Remember, even though there might be a really big shaft and a really little shaft, they're made out of the same material, which means the crystal sizes are the same. So the number of crystals exposed to a high stress increases. So there's a much greater chance in the bigger shaft that that a micro crack will form. Hence, the endurance, the Marin factor, or the the Marin factor, or the endurance limit modification factor, for a large shaft is less than it is for a small shaft. All right, and then surface finish. This is probably the biggest one, or certainly the most impactful. And reliability factors based on normal distribution stuff. It's not just made up, although the table that we're going to see makes it look like it's made up. And then here's a summary of all the Marin factors. The surface factor comes from a plot. The rest of them are kind of neatly summarized here. This isn't the only way to do it. There are more elegant or more complicated ways to do it, but this is pretty good. So we're going to stick with this. All right, now, that was a long review, but I think worthwhile. Now let's look at mean and alternating stresses. All right. So if in the RR Moore bending test, right, they're full reverse. It goes from full compression to full tension to full compression to full tension. If I have something that's not loaded fully reverse, such that there's a mean stress, right? So this is, this is the mean stress, and this is the alternating. Right, what's an example of something that has a mean and alternating stress? What about, so, yeah, I can't think of an example right now on the spot, but say like a swing, right? There's never, the chains on the swing, okay, how about yeah, let's do, I'll write that down. Example, chains on a swing set, right? What would that look like? Well, they're never in compression, so they go from 0 when there's nobody sitting on it to maximum when they're swinging, and then 0 when there's nobody sitting on a maximum, 0, maximum, 0, and maximum, like this. So a kid on swing set would be here, and then empty would be there, right? So this is not a fully reversed loading. This is a repeated loading. So we have the mean stress would look like this, sigma mean, and then this part up here would be sigma alternating, right? Now, and there's a bunch of formulas and stuff here, but again, I don't like formulas. Think about it. Just think about it. It has to be the mean stress is the average of the max and the min. And the alternating is the difference in the max and the min divided by 2, or the amplitude. Right? We in trigonometry, we'd call this amplitude. And then in circuits, we would call this a DC offset. For those of you who had ME 201 with me, when we used the oscilloscope, DC offset was one of the things we saw. Okay, so mean and alternating stresses, right? And this would be called, this one here is called repeated. Right, not fully reversed, repeated load. Right, so it goes from 0 to max to 0 to max to 0 to max. Okay, so hopefully that makes sense. Now, apples to apples, oranges to oranges. Many of you did, some sort of a problem back in your high school algebra class where you've got a machine that can make so many jelly donuts and then so many Bismarcks, and you got to maximize your profit. And if you have this one machine that can do this part and this other machine that can do this part, and you do these kind of problems. I love those problems. I don't know why. I just thought they were great. But both stresses, mean stresses and alternating stresses, affect the life of our part. And so what we do is we have to compare the mean stresses to the ultimate strength, right? And then we compare the alternating stresses to the endurance strength. And if we draw a line from, this is a terrible plot here. Holy cow. So this is sigma alternating, and this is sigma mean, right? So I just go, I figure out what my mean stress is, I figure out what my alternating stress is. So this is sigma mean, sigma alternating there. And that kind of helps me figure out what the life of my part will be. Well, I'm well below my ultimate stress. I'm well below my yield stress. I'm well below my endurance strength, or yield strength, ultimate strength, and endurance strength. Therefore, I would expect this part to last forever. So anywhere in this region down here, this is the infinite life region. Right, this part will last forever, okay? But it's important that we compare mean stresses to ultimate strength and alternating stresses to the endurance strength, right? Okay, so this is another way to look at the same data. These are all experimental data. It's important to note that this is 0 here. Here's 0. Like that. And then here we have, this is actually sigma equals SU. And this is, let's erase that. That didn't mean to erase that much. This is sigma equals Sn, right? Compression, look at, things tend to last forever. They never really fail. But what they do, okay, so yeah, let's just leave it at that. I got a piece of debris on my iPad here. Oop, there we go. And so we discovered that if we do plot this, if we plot the stress applied and then, or the combination of stresses, and then run it to failure, we discover that it does actually fall on this line from, so, that was terrible, never mind, skip that, maybe I'll edit this out. All right, and again, I can't stress enough, all models are wrong, right? Some are useful. There's a bunch of different ways to do this. First of all, for the most part, we're concerned with yielding, right? So we need to avoid yielding. We need to avoid the yielding there. And then there's multiple models that we could use. There's this ASM elliptic line. There's the Gerber line. There's the modified Goodman line. All these different models to kind of plot mean stresses and alternating stresses and compare those to infinite life. But we're just going to use the simplest one, right? Thank you very much. This is the one we're going to use. Easiest one. All right, so first of all, we're using the easiest model, and that's the stress life model, and then we're going to use the easiest model within that subset, and that's a Goodman line, and that's just a straight line that goes from endurance strength to ultimate tensile strength versus some of these elliptical lines. This one's kind of nice, actually. This includes yield failure. So maybe in future semesters I'll take a crack at that one. But Goodman just makes the math so easy. I want to test your engineering skills, not your math skills. Yeah, so anywhere in here is, let's do this in green. This is all infinite life in here. Right, so that's infinite life, no yielding. And this over here would be yielded, but no fatigue failure. Now you might say, that's dumb. Why'd you make a part that can survive, the repeated loadings or the alternating stresses, but it yields? We're going to look at that when we look at bolts and fasteners. right? I don't care if a bolt yields a little bit, right? As long as it's still holding. But we do like them to have really high tensions. We'll talk about that more later. All right, and so there's a bunch of key equations. Remember, there's all these different models: Gerber, ASME elliptic, and then the modified Goodman. We're only going to look at this one, and this is a super easy equation to use. So this is super easy to use. And this here is the safety factor. Against infinite life. Right. So you just plug the stuff in. You know your alternating stress, you know your endurance limit, you know your mean stress, you know your ultimate tensile strength. If you know all that stuff, you can get your safety factor. Or, you know, obviously you can solve for any one of these if you know the others, which is what you're going to have to do for your project, and I think even one of your homeworks. All right. So remember at the very start of the last lecture, we said stress concentrations matter, right? In static loading, in ductile materials, we don't worry about them because some of the fibers will stretch, they'll yield, if you will, and then the load gets picked up by the neighboring material. In brittle materials, that doesn't happen, right? It doesn't yield, it fractures, right? And then that fracture propagates. So stress concentrations in static loading in brittle materials is very bad. What about ductile materials in fatigue? Okay, they're bad, but they're not that bad, right? So let's take a look. So this is, KF is called the fatigue stress concentration factor, and KT is theoretical from tables and plots, right? So what is it that makes the fatigue stress concentration factor, or in general a stress concentration factor, bad? It's the fact that it's bigger than 1. All right, so what do? We take the 1 away, so we have this KT minus 1, so say the stress concentration factor was 1.6. Well, we say, all right, it's just the 0.6. All right, the 0.6 is the part that really matters. We multiply that by this Q, which is notch sensitivity. Now I'm running out of room here. So the Q is notch sensitivity. Right, so it really, Q is a measure of how bad is, or how much of an impact does the stress concentration really have on this part, right? So, for instance, if KT was 1.6, yeah, so KT equals 1.6. So example here, Q equals, let's see, 0.9 is kind of typical. Then the fatigue stress concentration factor would be the 0.9 times the 0.6, which is 0.54. You add that back on, so you get a 1.54, right? So the notch sensitivity, it's usually not 1, right? It's usually less than 1. So the stress concentration factor isn't as bad as the 1.6. In fatigue, it only winds up being a 1.54, okay? Now, this is for normal stresses. All right, there's another one for shear stress. And so both of those are on the same page in your book. So, general procedure for fatigue failure. Find the principal strengths of your material, right? What's ultimate tensile strength? And you got to go through the process with all these Marin factors and figure out what the endurance strength is. Find the stresses involved. We're going to use distortion energy to find an equivalent stress, all right? Find the theoretical stress concentration factor. So we need to do that. I mean, need to make a comment here. Let's do that in blue. So I need K. No, I'm going to erase that. I'm going to write it this way. For both sigma and tau, right? So we have shear, normal, and shear, right? Find the notch sensitivity for the material, right? for normal and shear. All right, and then we multiply those, or then we get the KF, right, from equations. So KF equals 1 plus Q times KT minus 1. And then use the Goodman equation to find the safety factor. We talked about that. Now, if the safety factor is less than 1, it will fail after some number of cycles. But we'll talk about that not next week, next lecture. So what is that number? Oftentimes we're interested in that. Okay, so you've got some homework to work on that I think you're able to do, and this is tough stuff. You just got to go through the process, right? But again, you know, look at it's the same in 6E too. At section 8.17, it kind of steps you through the whole process. There's a lot of good examples. So watch Alston's example videos. Try the homework. Ask me during office hours. You just got to practice this stuff. Okay, I think that's it. Yeah, that's it. We'll see you later.